Somewhere in the world tonight, a single particle is quietly refusing to be in only one place. It slips through two doorways at once, interferes with itself, and only settles into a single answer when something finally looks. That gentle impossibility is where we are wandering this evening, here on Midnight Science. Before we drift in, tell me softly, where in the world are you settling from? And what hour has found you tonight? And if this sleepy little corner has kept you company before, a quiet like and subscribe helps it keep drifting along. Somewhere in the room where you are, there is a cup. It might be resting on a table beside you, or on a shelf across the room, or sitting on the floor by the sofa where you quietly gave up on drinking whatever was inside it an hour ago. Wherever it is somewhere. That is the small, unspoken agreement between you and the objects around you, an arrangement so ordinary that you have never once had to think about it. The cup is on the table. The lamp is beside the sofa. The shoe you kicked off earlier is by the door, or a little short of the door, or nudged against the leg of a chair in the general direction of the door. And the sleeping animal, if there is one in your life, is curled on the chair, or the rug, or the corner of the bed you have quietly ceded to them. Each of these things is in exactly one place. Each of these things is being exactly one thing. You do not have to check. You do not have to walk over and confirm. You simply know, in the calm background way that you know most things, that the world has arranged itself into a soft grid of locations, and that the objects in your room are honoring that grid without any effort on your part. This is such a quiet fact of daily life that it barely earns a name. Physicists sometimes call it definiteness, which is a rather stiff word for something so gentle. It is the sense that everything that exists is somewhere, that everything that is a thing is one thing, and that even when you are not paying attention, the world is quietly holding on to its own arrangement without needing to be reminded. The cup does not slip into being on the shelf while you are looking away. The lamp does not become the shoe. The sleeping animal does not gently unravel into a mist of possible positions across the chair. Everything stays where it is, doing what it is, waiting to be found again exactly as it was left. This is, when you slow down enough to notice it, an extraordinarily comforting arrangement. Almost all of the peace of an ordinary room depends on it. The whole idea of home rests on this quiet reliability, that the walls will still be walls when you wake, that the mug on the counter will still be the mug on the counter, that the book you closed and set down will not have wandered off to reconsider its own edges. Tonight, gently, we are going to loosen that comfort. Not roughly, not all at once. Just a little, in the way you might loosen a scarf when you come indoors and realize the room is warmer than the street. The world will still be here. The cup will still be there. Nothing in your room is about to misbehave. But underneath the ordinary surface of your evening, there is a strangeness that the smallest pieces of the world have been carrying quietly all along, and tonight we are going to spend some time softly noticing it. Before we do, though, let us stay with the ordinary world for a little longer, because it deserves the attention. There is something almost tender about how confidently your room presents itself. If you were to close your eyes right now and try to picture your surroundings, you would find that your mind places each object in a definite spot with almost no effort. The cup is here, the lamp is there, The shoe is by the door, and the animal is on the chair. Your mind does not offer you a shimmering cloud of possible cup positions from which you must select. It hands you a single arrangement, quietly assembled, and expects you to accept it. And you do accept it. You have been accepting it all your life. Consider, softly, how deeply this intuition runs. Imagine, if you will, a coin in a pocket. Not a coin being tossed, not a coin spinning in the air, just a coin resting quietly in the fabric of a coat that has been hanging on the back of a chair since the afternoon. You do not know, at this moment, which face of the coin is upward. You could not tell someone. If asked, you would shrug, and yet you would not, for even a small, quiet second, believe that the coin does not have a face upward. You would take it as an ordinary fact of the world, that the coin is either heads or tails, right now, in that pocket, whether or not anyone knows. Your ignorance about the coin is one thing. The coin's own condition is another. The coin, you would say, has an answer. You simply do not have it yet. This is such a natural way of thinking that it feels almost silly to spell it out. Of course, the coin is one way or the other. Of course, things have their own facts, whether or not anyone is looking. Of course, the world is not waiting on your attention to decide what it is doing. And in the world of coats and coins and cups and shoes, this intuition is exactly right. It has never let you down. It has never given you a strange result. It has been the reliable background music of your entire life. Consider another everyday example. A key on a shelf. You put the key there this morning, or yesterday, or 2 evenings ago, and it has been there ever since. You have not looked at the shelf in hours. You have not walked past it. The key has been quietly unobserved for what might as well be an eternity from the key's perspective, if a key had a perspective. But even without checking, you would say, without hesitation, that the key is still on that shelf, that the key has a definite position, resting in a definite spot, whether or not anyone has laid eyes on it. If asked, you would not describe the unobserved key as being in a soft cloud of possible positions on the shelf. You would say, it is there, where you left it, doing its quiet, unremarkable job of being a key. And when you eventually go to fetch it and find it exactly where you thought it would be, this will not surprise you. It will not feel like a coincidence. It will feel like confirmation of something you already trusted. The key was there because keys are somewhere, because things are things, because the world is quietly definite and always has been. This whole gentle structure of expectation is what we are going to examine tonight. Not to tear it down, not to alarm you, but to notice softly that at the smallest scales of the world, this arrangement quietly does not apply. That at the level of the tiniest pieces of matter, the pieces that make up your cup and your lamp and your shoe and the animal on the chair, the assumption of one thing in one place turns out not to be a fact of the universe. It turns out to be something else, something stranger, something the world only offers you at scales large enough not to embarrass anyone. Now, this can sound alarming when written down in a hurry, so let us handle it gently. Nothing about your room is going to change. The cup will remain on the table. The lamp will remain beside the sofa. You are not going to look up during this video and find your shoe has drifted into a fog of possible shoe locations across the hallway. That is not what any of this means. The strangeness we are going to walk through tonight lives at scales so small that no ordinary object ever has to answer for it. Your world will stay exactly as solid as it has always been. The peculiarities we are going to visit are quiet peculiarities. They do not raise their voices. They do not rearrange your furniture. They simply exist, softly, beneath everything, in a way that most people never think about because the world above them is so calm and so definite that there seems to be no reason to look further. But tonight, there is a reason. Tonight we are going to look further, not far enough to become uncomfortable, just far enough to notice something remarkable about the world you have been living in all along. Let us begin the descent gently. Everything you see in your room is made of atoms. This is a fact so often repeated that it has almost stopped meaning anything. But pause with it for a moment. The wooden leg of the table, the ceramic wall of the cup, the fabric of your blanket, the fur of the sleeping animal, the metal of the shoe's small buckle, all of it, without exception, is made of small pieces, almost impossibly small pieces. Pieces so small that if you tried to line them up along the width of a single strand of hair, you would need somewhere in the neighborhood of 1 million of them to reach across. And each of those atoms is itself made of even smaller pieces, a nucleus gently held together in the center, a cloud of electrons softly drifting around it, and the nucleus itself made of protons and neutrons, which are in turn made of even smaller pieces still, though we are not going to visit those tonight. Tonight we are simply going to notice that your room, in its calm solidity, is made of things you have never seen, moving in ways you have never observed, obeying rules that are not the rules of tables and cups. And it is here, at this level, that the ordinary intuition begins to fail. The electrons in your cup are not, at any moment, sitting quietly in one place. They are not tiny beads. They are not miniature marbles running along tiny tracks. They do not have a location in the way that the cup itself has a location. And yet the cup is made of them. That is the small, quiet paradox at the heart of tonight. Your entire room is built out of pieces that do not, in the calm daily sense of the word, live in single places. The cup has an address. The electrons that make it up do not. Let this land softly. It is not a claim about the physicists being confused. It is not a claim about the equipment being too crude. It is a claim about the world itself, quietly, at its smallest levels, being something other than the arrangement of things in places that your intuition insists on. The particles that will keep us company tonight are two in particular, the electron and the photon. Think of them as gentle companions who are going to walk with us through the strangeness. The electron is a small piece of matter, part of every atom in your room, part of every object you have ever touched. The photon is a small piece of light, the thing that carries brightness from the lamp beside your sofa to your eyes, the thing that lets you see the cup on the table. Both are so small that no eye has ever seen one directly. Both are, when studied carefully, the softest possible troublemakers. Neither of them behaves, like a marble. Neither of them behaves like a coin in a pocket. Neither of them, when you look away, sits quietly in a single spot doing a single thing. And yet, together, they and their small relatives are what everything in your room is made of, and everything you can see it by. We are not going to open all of this up tonight. We are going to walk into it slowly, gently, one small step at a time, in the way you might walk into a cool room from a warmer one. There is no rush. There will be time to sit with each strange piece of the picture before we move on to the next. And if at any moment your attention drifts, if the animal on the chair does something more interesting than the physics, if the blanket becomes warm enough that your eyes close, that is entirely fine. The ideas will still be here when you find your way back. The cup will still be on the table. The lamp will still be beside the sofa. And the world, for reasons we are going to explore, will still have arranged itself into the calm daily grid you have been living inside all your life. For now, though, let us hold the picture as it stands. Your room is quiet. The objects in your room are in definite places. The intuition of definiteness, the sense that things are somewhere, whether or not anyone is looking, is the calm background of your evening. This intuition has never failed you at your own scale. It has been reliable your entire life. It will continue to be reliable long after this video ends. And yet, at scales small enough to disappear from any ordinary way of noticing, the world is doing something different. It is not being a coin in a pocket. It is not being a key on a shelf. It is not honoring the small unspoken agreement between you and your things. Beneath the calm surface of the room you are sitting in, the particles that make up the cup and the lamp and the shoe and the animal on the chair may not, in any honest sense, agree that they are anywhere in particular. And this is not because they are hiding their positions from us. It is because the concept of a position, the concept of being in one place doing one thing, is quietly loosened at the scale where they live. That last sentence will do a lot of work for us tonight. Sit with it for a moment. It does not say that the particles are somewhere we cannot see. It does not say that the particles are jumping too fast for us to catch. It says something gentler and stranger. It says that the very idea of a particle being in one place may not describe how the particle actually is before anyone looks. You do not need to accept this yet. In fact, please do not accept it yet. It is far too early in the evening for such a claim to land. Simply hold it softly, as a hint, as a possibility, as a small, unfamiliar note in the otherwise ordinary song of your room. We are going to spend the next several parts of this video quietly building up to that hint until it becomes something you can carry lightly, the way you might carry a small warm stone in a pocket. For now, it is just a suggestion, arriving from the smallest corners of the world, whispering that the intuition of definiteness may be true only in the sizes of things that have cups and shoes. And it is worth noticing, before we go any further, how strange this already is if you take it slowly. Everything you are, everything you can touch, everything you have ever seen is made out of the very things that seem not to honor the arrangement your daily life takes for granted. You are, in a very literal way, built out of pieces that do not, in the ordinary sense, live in single places, and yet you are here, in one place, on one sofa, wrapped in one blanket, watching one video. Somehow, the world assembles itself out of pieces that refuse to commit to positions, into rooms and cups and animals and evenings that keep their agreements perfectly. That is one of the loveliest small mysteries in all of physics, and we will come to it later in the night. For now, let us stay with the ordinary. Let us stay with the cup on the table, the lamp beside the sofa, the shoe by the door, and the sleeping animal on the chair. Let us notice how obvious it feels that each of these things is in exactly one place. Let us notice how peaceful that obviousness is, and let us gently make room in the corner of our attention for the small, unfamiliar possibility that this obviousness does not go all the way down, that beneath the calm surface of the room, the particles are keeping a different kind of arrangement, that the definiteness of your world may be a very soft trick that the universe plays for its own reasons, at your own scale, so that evenings like this one are possible at all. We will come to what that means in the parts to come. We will meet the double-slit experiment, which is the calmest possible demonstration that the intuition of one place at one time is wrong. We will meet the wave function, which is the gentle mathematical companion physicists use to describe the world before it commits to answers. We will meet Erwin Schrödinger and his famously unbothered cat. And we will meet decoherence, the very quiet reason your cup remains a cup, even though the pieces of it, on their own, do not seem to want to. But that is for later. That is for the slower hours of tonight. For now, we are still here, in the ordinary room, with the ordinary objects and the ordinary intuition. The cup is on the table. The lamp is beside the sofa. The shoe is by the door. The animal is on the chair. And you are wherever you are, hopefully warm, hopefully settled, hopefully able to listen without needing to keep track of every word. The world, for now, is behaving exactly as it always has. Only, perhaps, a little more mysteriously than it has been letting on. And that, softly, is where we begin. So, let us turn now to an experiment. Not a dramatic one, not a loud one, not the kind that lives in museums behind velvet ropes or gets described with urgent music playing underneath it. The experiment we are going to visit tonight is one of the calmest ever performed. It has been done for more than 200 years, in one form or another, in quiet laboratories around the world, by patient people using small pieces of equipment and a great deal of care. And it happens to be the single clearest demonstration that the intuition we spent the last part settling into, the intuition of one thing in one place at one time, is not how the world works at its smallest scales. To meet it properly, we have to go back to the early 1800s, to a small room in England, and to a man named Thomas Young. Young was, by any measure, an unusually gentle sort of person. He was a physician by training. He was a scholar of ancient languages, part of the small, quiet effort that helped decipher the Rosetta Stone. He was interested in almost everything, and in the year 1801, he became curious about light. Not curious in a hurried way, curious in the slow, patient way that leads a person to sit in a room for hours, arranging small pieces of card until they line up just so. At the time, there was a long, unresolved argument in physics about what light actually was. Isaac Newton, who had shaped so much of the field, had argued that light was made of tiny particles. He called them corpuscles, which is an oddly medical-sounding word for something so bright. And for a long time, this picture held, partly because Newton had proposed it, and partly because it seemed to fit certain simple observations. Light travels in straight lines. Light casts sharp shadows. Light bounces off mirrors in tidy ways. All of this looks, on the surface, like the behavior of very small marbles zipping through the air. But other thinkers had suggested that light might be a wave instead, a ripple, something like the pattern that spreads out on the surface of a pond when a stone is dropped in. This idea had never quite gone away, and Young, working quietly in his rooms, decided to see whether he could tell the difference. His approach was elegant, in the way that only the simplest ideas ever are. If light is a wave, he reasoned, then it should behave like a wave when given the chance. And there is a particular thing that waves do when two of them meet that particles cannot do at all. Imagine, for a soft moment, a very still pond. If you drop a single stone into it, ripples move outward in gentle circles. Nothing surprising there. But if you drop two stones at the same time, close together, something quietly beautiful happens. The two sets of ripples move outward and pass through each other. Where two crests meet, they add together and make a taller crest. Where two troughs meet, they add together and make a deeper trough. And where a crest from one set meets a trough from the other, they cancel out, and the water in that spot stays flat. The result is a pattern of raised places and calm places, arranged in a soft, striped shape across the surface of the pond. This pattern is called interference. It is one of the quietest and most reliable signatures of a wave. Marbles do not do it. Coins do not do it. Only waves do. Young wanted to know whether light would do it. So he took a small source of light, and in front of it he placed a screen with two narrow slits cut into it, sitting very close together. Behind that screen, at some distance, he placed another screen, a plain one, on which the light could land, and he waited to see what would appear. If Newton was right, if light was made of small particles, then the answer would be simple. The particles would travel from the source. Most of them would be blocked by the first screen. Some would pass through one slit, some would pass through the other, and behind the second screen you would see two soft, bright stripes, one behind each slit, corresponding to the two openings the light had come through. That is what you would expect if you were throwing tiny marbles through two doorways. Two piles of marbles on the far wall, one behind each door. Simple, ordinary, definite. That is not what Young saw. What he saw, instead, on the far screen, was a pattern of many bright and dark stripes, arranged in a soft, even rhythm across the surface. Not two bright places, many, alternating with dark places where no light seemed to have arrived at all. This was exactly the striped pattern that waves make on the surface of a pond. It was interference, and it meant, gently and undeniably, that light was behaving like a wave, that the light passing through the two slits was spreading out from each opening, meeting on the far side, adding where crest met crest, cancelling where crest met trough, and leaving that soft stripe record of its own passage. Young published his result, and it slowly began to reshape the way physicists thought about light. Over the next century, this picture of light as a wave became one of the central pillars of physics. The equations that describe waves were used to describe light in extraordinary detail, and they worked beautifully. If you had asked any physicist in the 1800s what light was, they would have said, calmly, that it was a wave, and they would have pointed to Young's little experiment with the two slits as one of the reasons they were so sure. And then, softly, and with no particular fuss, the 20th century arrived and complicated everything. Because in the early 1900s, physicists began to notice that light, in certain quiet situations, also behaved as though it came in small discrete lumps, as though it were, in some sense, made of particles after all. These lumps were given the name photons, and they arrived carrying just the right amount of energy each time, in tidy small packets that were hard to explain if light were only a smooth wave. So light, it seemed, was somehow both a wave when it moved, a particle when it landed. This was already strange, but the deeper strangeness was still coming. The deeper strangeness arrived when physicists began to wonder what would happen if you performed Young's experiment, not with a beam of light containing countless photons all together, but with single particles, released one at a time. Not just single photons, but single electrons too, sent through the same kind of two-slit arrangement, individually, so slowly that there was only ever one particle in the apparatus at any given moment. The reasoning was gentle. If light behaves like a wave because many photons are traveling together and interfering with each other on the far side, then sending them one at a time should stop that from happening. A single photon, all alone, has nothing to interfere with. A single electron released into an otherwise empty apparatus is a small solitary thing, moving from one place to another. It should behave like a marble. It should go through one slit or the other and land somewhere on the far screen, and that would be that. And if you did this many, many times, sending single particles one after another, you should build up, on the far screen, exactly the two bright stripes Newton would have predicted. Two piles of marble marks, one behind each slit. Nothing else. That is what should happen. It is the calm, ordinary, intuitive prediction. It is the answer that fits the way your cup sits on your table. That is not what happens. What happens when the experiment is actually performed is one of the quietest and most unsettling things in all of physics. Each individual particle, released alone, travels through the apparatus by itself and lands somewhere on the far screen, leaving a small mark where it arrived. Just one small mark, in one place, perfectly definite, perfectly ordinary looking. If you saw a single one of these marks, you would think nothing of it. It looks exactly like the arrival of a small solitary thing. But then you send another particle, and another, and another, slowly, patiently, one at a time. Each one is alone in the apparatus. Each one leaves a single small mark. And as the marks accumulate, something extraordinary begins to appear on the far screen. Not two stripes, not a random scatter, but the same soft striped pattern that Thomas Young saw 200 years ago. Bright bands, dark bands, alternating gently across the surface. Interference, the signature of a wave. the pattern that a wave makes when it meets itself, arriving mark by mark from particles that were sent one at a time, alone, with nothing else to interfere with. Let this land softly. It is worth staying with. Each particle, on its own, produced a single mark, as though it were a small, definite thing, fine, ordinary. But the collection of those single marks, taken together, arranged itself into a pattern that only a wave passing through both slits could make, which means, gently, that each single particle must have traveled through both slits at once, that it must have spread itself, somehow, through both openings, that it must have interfered with itself on the far side before finally landing at some particular spot on the screen. There is no other way to make the pattern. Waves interfere because two parts of the wave meet. If only one particle is present, then the only way for interference to happen is for that one particle to be, in some sense, in two places at once as it moves through the apparatus. To have gone through the left slit and the right slit simultaneously, to have carried both possibilities forward together, to have quietly refused to be a small, solitary thing while it was moving. Restate this gently. A single particle passing through a screen with two openings in it does not go through one opening the way a marble would. It behaves, while in flight, as though it went through both, and the evidence for this is not indirect. It is written in the pattern of marks on the far screen, mark by patient mark, in a signature that only a wave interfering with itself can produce. This is the calmest possible demonstration that the intuition of one thing in one place at one time is wrong. Not wrong for exotic objects, not wrong in some hidden corner of the universe. Wrong for the very things that make up your cup, and your lamp, and your shoe, and the sleeping animal on the chair. The particles that build your world do not, when moving, honor the arrangement your daily life takes for granted. They spread. They travel through more than one path at once. They interfere with themselves. And they do this quietly, without any fuss, in laboratories all over the world, whenever anyone patient enough sets up the right small pieces of equipment. Let us sit with this for a moment, because it is easy to hurry past it, and this experiment deserves a slow attention. Everything else in tonight's story rests on it. If you take nothing else from this evening, take this. A single small piece of matter sent through a screen with two openings does not, on its own, pick one. It goes through both. It arrives on the far side, having somehow traveled two paths at once, and it leaves behind, after enough repetitions, a striped pattern that could not exist if it had done anything else. It is a very gentle result. Nothing about the apparatus is dramatic. Nothing about the particle is dramatic. There is no explosion. There is no flash. There is simply, over many patient hours, the slow accumulation of marks on a screen, arranging themselves into a signature that quietly contradicts the intuition of definiteness. It is one of the softest disturbances in all of physics, and it is one of the deepest. Now, the story does not end here. There is a further twist to this experiment, and it is the twist that has haunted physicists for more than a century, and it is the twist we need to walk into now, gently, because it is where the strangeness deepens. Because at some point, someone thought to try something reasonable. They thought, Well, if the particle is somehow going through both slits at once, we should be able to check. We should be able to place a small detector at each of the two openings, some careful device that can quietly notice when a particle passes through it, and simply watch. Just watch. Not disturb the particle in any harsh way. Just observe, gently, which slit the particle went through on its way to the far screen, and then perhaps we will finally have caught the strangeness in the act. We will see, mark by mark, which slit each particle really used, and we will finally understand what is happening. So the detectors are set up, the experiment is run again, the single particles are released, one at a time, and this time, at each opening, a small quiet instrument records whether the particle passed through. Each particle is watched at the slits. Each one is noted. Each is followed on its journey, and the pattern on the far screen quietly disappears. Not partly, not weakened, the pattern is gone. In its place, on the far screen, are the two soft stripes that Newton would have predicted from the very beginning. Two piles of marks, one behind each slit, exactly the marble-like behavior that the original experiment had denied. The interference pattern, the wave signature, the evidence that the particle had traveled through both openings at once has simply and quietly vanished. Let this land without alarm. The equipment is fine. The detectors are gentle. The particles are the same particles. Nothing has been broken, nothing has been damaged, nothing has been forced. The only thing that has changed is that someone, or something, is now noticing which slit the particle goes through, and that noticing, that soft act of watching, seems to change what the particle does. When the particles are unwatched, they behave like waves, going through both slits, interfering with themselves, building up the striped pattern. When the particles are watched, they behave like small, definite things, going through one slit or the other and building up the two stripes. The very same particles, in the very same apparatus, doing the very same journey, arrange themselves differently depending on whether or not the passage is being observed. Restate this gently, in slightly different words. If nobody is looking at the slits, the particle behaves as though it went through both. If somebody, or some detector, is looking at the slits, the particle behaves as though it went through one. The particle appears to notice whether it is being noticed. The world appears to arrange itself differently depending on whether it is being watched. That last sentence is doing an enormous amount of quiet work, and it is very important that it is not read too dramatically. This is not about consciousness. It is not about human minds having magical powers over matter. It is not about the universe caring whether you personally are paying attention. The detectors in these experiments are not human eyes. They are small pieces of equipment, cameras, sensors, tiny devices that record without any dramatic ceremony. The strangeness is not that human awareness changes reality. The strangeness is that any interaction that would let anyone in principle know which slit the particle went through seems to be enough to collapse the pattern. It is the possibility of knowing, not the knowing itself, that matters. We will come back to this. We will come back to what measurement means and why it seems to have this quiet power, and how physicists have tried to make peace with it over the last 100 years. That is later in the night. For now, let this simply sit as the second half of the strangeness. Not only does a particle travel through both slits at once when unwatched, it also stops doing so when watched. Both halves are equally real. Both halves have been confirmed in laboratories many times, in many different setups, with many different kinds of particles, from photons of light to electrons to whole atoms and even small molecules. This is not a fragile result that appears only in delicate conditions. It is one of the most reliably reproduced phenomena in all of physics, and it is one of the strangest. You do not need to make peace with it tonight. You do not need to resolve it. The physicists themselves have been sitting with this for over a century, and they have arrived at various patient understandings without fully settling the matter. What you can do, softly, is let it stand as an observed fact of the world, a fact so gently confirmed that no serious physicist doubts it, a fact so quietly strange that no ordinary intuition survives contact with it, a fact that the smallest pieces of your cup and your lamp and your shoe and the sleeping animal on the chair have been carrying quietly all along without ever bothering to mention it. Perhaps the calmest way to hold this, at least for now, is to notice what it does not say. It does not say that the particle is jumping between the two slits too fast for us to catch. It does not say that we simply have not built good enough detectors. It does not say that the physicists are confused, or that the equations are broken, or that the equipment is faulty. The equations describe the behavior beautifully. The equipment works exactly as it should. The physicists, on the whole, are calmer about all of this than one might expect. What the experiment says, gently and repeatedly, is that the world at its smallest scales does not honor the intuition of one thing in one place at one time, and that looking at it in the sense of allowing an interaction that could reveal which path was taken quietly changes what the world does. And so we arrive, softly, at the pivot of tonight. The particle is not secretly here or there before it lands. It is, in some real way, both, until something interacts with it. The interference pattern is the fingerprint of that bothness. The disappearance of the pattern under observation is the fingerprint of that bothness, collapsing into a single answer. These are not two separate mysteries. They are two sides of the same very gentle strangeness. The cup is still on the table. The lamp is still beside the sofa. The shoe is still by the door. The animal is still on the chair. Nothing has moved. Nothing has changed. But underneath the calm surface of your room, the particles that build these objects have been going through both slits when nobody was watching, quietly, for as long as there have been slits to go through. That has been the arrangement all along, and in the next part of tonight, we will give this arrangement its proper name and try, very softly, to understand what it might mean. The experiment we walked through in the last part has been done, in one form or another, for well over a century. It has been repeated by many quiet, careful people, with many quiet, careful pieces of equipment, in many quiet, careful rooms, and each time it has been repeated, the same soft strangeness has appeared. So at some point, someone had to give this strangeness a name, a gentle handle, a word you could reach for when you needed to talk about what the particle was doing in those unwatched moments between leaving the source and landing on the screen. The word they settled on is superposition. It is, admittedly, a slightly stiff word for something so soft. It sounds like the name of a very organized office chair, or perhaps a technique in ballroom dancing. It does not arrive carrying a basket of friendliness, but it is the word the physicists use, so we will use it too, and we will treat it gently, and we will spend this part of tonight quietly unpacking what it means. Because more than any other single idea in quantum physics, superposition is where the intuition of your daily life must be softly set down for a while, not thrown away, just set down. It will be waiting for you exactly where you left it when the video ends. The first thing to say about superposition, and perhaps the most important thing to say, is what it is not. There is a very reasonable, very natural, very human way to hear about the double-slit experiment and to arrive at the following calm explanation. The particle really did go through one slit. It just went through one slit that we, in our ignorance, could not identify. The particle had an answer all along. We simply did not have access to it. This is the coin under the cup interpretation. You know the setup. Someone tosses a coin, catches it, and covers it with a cup before you can look. The coin under the cup is either heads or tails, right now, in the present moment. Even though you cannot see it, even though you have no idea which way it landed, the coin is one of the two. Your ignorance is one thing. The coin itself has a definite state. When you eventually lift the cup, you are not creating a face of the coin. You are simply learning which face was there all along. It would be so much easier and so much more comforting if this were what superposition meant. If the electron had really gone through the left slit or the right slit all along, and we simply, in our small human way, had not known which one, until the interference pattern forced us to admit our confusion. This is the interpretation that many people arrive at when the experiment is described to them for the first time. It feels like common sense. It preserves the calm background comfort of definiteness. It lets you keep your intuition intact. And it is wrong. This is the pivot of the whole night, and it is worth walking into slowly because it is easy to miss why. The reason the coin under the cup picture cannot be what is happening in the double-slit experiment is because of the striped pattern itself. If each particle had really gone through one slit, and we simply did not know which, then the pattern on the far screen should be the same as if we did know. Ignorance on our part does not change what the particles actually do. Coins under cups do not stop being heads or tails just because someone hid them. If the particles were secretly definite, the marks on the screen would build up into the two soft stripes that Newton would have expected, whether anyone was watching or not. The pattern would look the same whether we chose to install detectors or not, because our choice of instruments would not change the coin's own reality. But the pattern does change. That is the whole point. When nobody watches the slits, the striped interference pattern appears. When someone or something watches the slits, the pattern disappears, which means the particle's behavior depends on whether the passage is being observed, which means the particle was not, in the unwatched case, really going through one slit that we simply did not know about. Because if it had been, it would have kept doing the same thing regardless of our looking. The world does not adjust its facts based on our attention, but the world, at this scale, quietly does. So the coin under the cup picture is not what is happening. The particle is not secretly here or there before it lands. It is not carrying a hidden answer that our clumsy human perception fails to reach. It is doing something stranger and softer and more interesting. Superposition is what the particle is doing instead. The word, if you break it apart gently, means something like a laying together of possibilities, a layering, a soft, simultaneous presence of more than one option. In the double-slit experiment, the electron in flight is not on the left path. It is not on the right path. It is not on any one path at all. It is in a superposition of both paths. Both possibilities are equally present. Both possibilities are equally real. Neither has been chosen. Neither is hiding. There is not a hidden answer under the cup, because there is no cup, and there is no coin, and there is no fact of the matter waiting to be uncovered. Restate this softly, because it is easy to slide back into the old picture. The electron, while it is moving through the apparatus, does not have a definite path. It is not that we do not know its path. It is that its path is not one thing. The particle exists as a blend, a spread, a soft presence across both possibilities at once, and only when it is measured, only when something interacts with it in a way that would let anyone in principle know which path it took, does the blend gently collapse into a single answer. This is the strangeness that Thomas Young's little experiment carried, quietly, for 200 years, before anyone quite understood what it was saying. Now, if you try to picture superposition, your mind will do a very natural and very slightly misleading thing. It will try to imagine the electron as a small ghostly object hovering fuzzily between the two slits, half in one and half in the other, as though it were partly transparent. This picture is not quite right, but it is not entirely wrong either, and it is a gentle place to start. The particle is not a small ghost, but it is also not a small marble. It is something for which we do not have an ordinary word in the language of coats and coins and cups. The best we can do is describe it mathematically, and physicists have a lovely gentle companion for that, and its name is the wave function. The wave function is one of the most important ideas in all of quantum mechanics, and it is also one of the softest. It is a mathematical object, a kind of smooth spread across space and time that describes all the possibilities available to a quantum system. It does not tell you where the electron is. It tells you, at every point in space, how much of the electron's possible presence is there. Where the wave function is large, the possibility of finding the electron in that place is high. Where the wave function is small, the possibility is low. Where the wave function is zero, the electron will simply not be found. The wave function is not the electron. It is something more like the electron's soft cloud of possibility, arranged smoothly across the whole of the space it might inhabit. Now, here is the gentle part. The wave function evolves through time in a very calm and predictable way. There is an equation written by Erwin Schrödinger in 1926 that describes exactly how the wave function changes from one moment to the next. It is not a chaotic equation. It is not full of jumps or crashes. It is a smooth, wave-like equation, and it evolves the possibilities of the system slowly and steadily, in a way that is, in its own quiet way, quite beautiful. The wave function spreads. It ripples. It moves through space like a very calm wave on the surface of a very deep pond. And all the strangeness of quantum physics, all the double slits and the interference in the two paths at once, is described smoothly and precisely by this one gentle equation, which is, if you slow down long enough to notice, remarkable. The strangeness has a mathematics. The mathematics is calm. The equations do not panic. The physicists do not have to guess at what will happen. They simply solve the Schrödinger equation for a given situation, and it tells them exactly what the wave function will look like at any later time. The behavior of a single electron in a double-slit apparatus, the interference pattern that emerges over many patient repetitions, all of it is contained in the smooth evolution of that soft mathematical companion. There is nothing missing. The theory works, and it works with extraordinary accuracy. What the theory does not do, though, is tell you which single outcome will occur when a measurement is made. It tells you the shape of the possibilities. It tells you in soft probabilistic terms how likely each possible outcome is, but it does not tell you in advance which possibility the particle will settle into when someone finally looks. That last small step, the step from a spread of possibilities to a single answer, is not part of the smooth evolution. It is something else, something the equations do not fully describe. And it is where the deepest, quiet questions of quantum physics still live, more than 100 years after the wave function was written down. Let this land softly. The particle, before measurement, is described by a wave function that gently holds all the possible outcomes together. When measurement happens, the particle becomes one outcome. What exactly measurement is, and why it seems to have this effect, and what the wave function really is between measurements, are questions that physicists are still, in their calm, patient way, working through. But the mathematics itself is not in doubt. It has been checked and rechecked and rechecked again for a century, and it always works. Which brings us to the softest and strangest way of stating the whole picture, and it deserves its own moment. Measurement does not reveal a pre-existing answer. Measurement creates one. Sit with this for a moment. In the old comfortable picture, the picture of coins under cups and keys on shelves, measurement is simply the act of learning what was already true. The coin was always heads. You just did not know. The key was always on the shelf. You just had to look. Measurement is a peaceful uncovering of facts that were quietly there all along. In the quantum picture, this is not what measurement is. Measurement is something more like an act of selection. Before the measurement, the particle exists as a spread of possibilities, all of them equally real, none of them singled out. The measurement, whatever it is, whatever precisely happens during it, seems to pluck one of these possibilities out of the spread and make it the actual outcome. The other possibilities simply cease to be relevant. They do not become hidden, they do not go somewhere else. They just gently stop being part of the story, and the particle, from that moment on, behaves like a small, definite thing with a definite property, having been, until an instant ago, a soft blend of many. You can see why this has kept physicists gently up at night for 100 years. The people who first had to make peace with all of this were an extraordinary small group working in the early 1900s in a handful of universities across Europe. Erwin Schrödinger, whose equation we just met, was an Austrian physicist with an unusually poetic mind. He was more comfortable in the mathematics of waves than in the philosophy of what those waves meant, and he spent much of his later life quietly uneasy with the interpretations that other physicists were building on top of his equation. He is often remembered for his cat, which we will meet properly in the next part of tonight. But his gentler contribution is this soft mathematical companion, the wave function, evolving smoothly through time, holding all the possibilities together in one calm equation. Werner Heisenberg was a young German physicist, a few years younger than Schrödinger, who had arrived at the same underlying physics by a different mathematical route. Where Schrödinger thought in waves, Heisenberg thought in tables of numbers in what came to be called matrix mechanics. It turned out, eventually, that these two apparently different pictures were describing the same underlying theory in different mathematical languages. Heisenberg is also remembered for the uncertainty principle, which is a gentle piece of quantum physics that says certain pairs of properties, like position and momentum, cannot both be sharply defined at the same time. The more sharply you know one, the more softly the other must be described. This is not a limit of measurement. It is a feature of the particles themselves. The intuition of a small thing with an exact position and an exact velocity simply does not survive the trip down to the quantum scale. And then there was Niels Bohr, older than both of them, a Danish physicist who ran a small institute in Copenhagen, where much of the early work on quantum mechanics was thought through. Bohr was the calm philosophical center of the movement. He worked patiently, sometimes exhaustingly, on the question of what all of these equations were really saying about the world. He was gentle in conversation, endlessly patient in argument, and unusually willing to hold uncomfortable ideas in his mind for long stretches of time without demanding they resolve. It was largely through the discussions at his institute, over many quiet evenings and long walks and slow cigars, that the standard way of talking about quantum mechanics took shape. That standard way is often called the Copenhagen interpretation, after Bohr's home city. It says, in soft summary, that the wave function is a complete description of a quantum system before measurement, that measurement is a distinct kind of event that collapses the wave function into a single outcome, and that questions about what the particle is doing between measurements do not have straightforward classical answers. It is a careful, humble interpretation. It does not try to say too much. It respects what the mathematics does, and it accepts what the mathematics does not do. Not every physicist has been satisfied with it, and there are other interpretations we will not visit tonight. But the Copenhagen picture has been the quiet background of quantum physics for most of the last century, and it is the picture we are gently using in this video. Schrödinger, Heisenberg, and Bohr, along with a handful of others, spent long years trying to make peace with what their own equations were saying. They did not always agree with each other. They sometimes wrote each other very polite letters that gently disagreed, and sometimes wrote each other less polite letters that gently disagreed more forcefully. Schrödinger, in particular, was famously uncomfortable with the collapse of the wave function. He felt that if his equation described the world before measurement, it should also describe the measurement itself. And he did not like the idea that some measurements simply happened without being derivable from the equation. His discomfort is what led him, eventually, to his cat, which we will visit in the next part. But for tonight, in this part, what we are noticing is simply this. These were thoughtful, gentle, careful people, working slowly, without hurry, on the meaning of one of the most extraordinary discoveries in the history of physics. They did not resolve every question. They passed some of the questions on to later generations, who are still working on them today, quietly and patiently in institutes and universities around the world. And the picture they left us with is a soft picture, a picture in which the smallest pieces of the universe do not, before being noticed, live in single definite states. A picture in which the world beneath the world is not made of things in places, but of possibilities that only become things when something interacts with them. Let that sit for a moment. It is one of the strangest sentences in physics, and it is worth reading softly, more than once. The world beneath the world is not made of things in places. It is made of possibilities, and those possibilities only become things when they are noticed. That is what superposition means. Not that the particle is somewhere we cannot see. Not that the particle is jumping too fast for us to catch. Not that we simply lack the equipment to check. It means that at the scale where your cup and your lamp and your shoe and the sleeping animal on the chair are all made, the world does not commit to arrangements ahead of time. It holds them softly, as spreads of possibility, and only settles into a single answer when something interacts with it in the right way. This is why, no matter how carefully you set up the experiment, you cannot catch the particle secretly going through one slit. There is no secret to catch. When the particle is unwatched, it is not on the left, and it is not on the right, and it is not hiding some fact from you. It is in both, in the only way it knows how to be. It is a blend of possibilities that the mathematics describes with great precision, and that your intuition has no ordinary language for. And when the particle is watched, it is not that the equipment finally revealed the truth. It is that the interaction created one. The cup in your room is still on the table. Nothing has changed in the room. But the pieces of the cup, the atoms and the electrons and the small companions that make it up, have been living quietly in spreads of possibility all along. They have never, in the ordinary intuitive sense, been anywhere in particular except at the moments when the world has been noticing them enough to force an answer. And there is a great deal of quiet noticing happening in an ordinary room all the time, as we will begin to see later in the night. For now, though, the picture is enough. The particle was never really at one slit. The wave function is not our ignorance. It is a description of the world's own state before measurement. Superposition is the genuine, simultaneous presence of multiple possibilities. Measurement does not reveal an answer, it makes one. And beneath the calm surface of your room, softly, the world beneath the world is not made of things in places. It is made of possibilities, gently drifting, quietly waiting to be noticed. So we have arrived at a place where the smallest pieces of the world do not, before being noticed, live in single definite states. The electron is not secretly here or there. Its wave function is spread across possibilities, and only interaction plucks out a single answer. This is fine, in a soft sort of way, when we are talking about electrons. Electrons are not part of your ordinary evening. You have never seen one. You have never held one. You would not know how to. If electrons want to live in gentle blends of possibility, you can, with a little effort, let them. Your cup remains a cup. Your room remains a room. The strangeness stays quietly in the corner, where the very small things live, and does not particularly disturb you. But there is a soft question sitting underneath all of this, and Erwin Schrödinger, in 1935, decided to reach for it. He wondered, gently, What would happen if the strangeness of the small world were somehow dragged into the large one? If the blended states of a single atom were connected by some ordinary mechanism to something big, something we could see, something we care about, something with fur. And so, in a paper he was writing about the current state of quantum mechanics, Schrödinger introduced the most famous animal in physics. Before we meet the cat, we should meet Schrödinger himself again, because he deserves a proper introduction. He was Austrian, born in Vienna, and he had the sort of quiet, poetic mind that seemed to belong more to a 19th century philosopher than to a 20th century physicist. He wrote about biology, about consciousness, about ancient philosophy, in gentle books that were unusually readable for someone of his mathematical stature. He carried, throughout his life, a soft discomfort with some of the interpretations his fellow physicists were building on top of his own equation. He felt, with real feeling, that something was not quite right in the standard picture. And in 1935, in correspondence with Albert Einstein, he began to work out a way of making that discomfort visible to everyone else. The thought experiment he came up with is now known almost universally as Schrödinger's cat. And before we walk into it, one small thing, because it needs to be said gently at the start and not left to the end. No cat has ever been harmed by this thought experiment. No cat has ever been placed in a box. No cat has ever been threatened by a vial of anything. Schrödinger did not at any point conduct this experiment. The cat in the story exists entirely on paper. It is made of ink and mathematics and imagination. It has never breathed. It has never purred. It has never quietly walked across a keyboard while its owner was trying to write. It is a hypothetical creature, and it has enjoyed one of the most peaceful legacies imaginable, becoming the most famous animal in the history of physics without ever having to leave the page. Which is, when you think about it, a rather lovely retirement for a cat that never technically existed. With that small piece of care set down, let us walk into the box. The setup Schrödinger described is deliberately gentle in its parts and deliberately unsettling in its whole. It begins with a sealed box, not a small box, not a large box. Simply a box that is, for the duration of the thought experiment, closed. Nothing can be seen from outside. Nothing can be heard from outside. The box is isolated from the room in every way that matters, at least in the smooth, idealized way that thought experiments allow. Inside the box, Schrödinger places three things. The first thing is a small piece of radioactive material. This is a very ordinary sort of thing in the world of physics. Radioactive atoms are atoms that are gently unstable, in the sense that at some unpredictable moment they may quietly rearrange themselves and give off a small burst of energy in the process. This rearrangement is called radioactive decay. It is a quantum event, one of the softest and best studied ones in all of physics. And here is the important bit. Whether or not a given radioactive atom will decay in a given amount of time is not a matter of hidden facts. It is not that the atom secretly knows when it will decay and simply refuses to tell us. It is that the decay itself is genuinely uncertain in exactly the way we have been describing all night. The atom exists before observation in a superposition of two possibilities: decayed, not decayed, and the passage of time causes the wave function to slowly evolve, spreading more of its weight into the decayed possibility and less into the not decayed one. But at any given moment, before anyone looks, the atom is genuinely in a blend of both. Schrödinger arranges the amount of radioactive material inside the box so that, over the course of 1 hour, there is exactly a 50-50 chance that at least one atom will have decayed. This is a very clean quantum coin toss. If we do not open the box, the atom is, at the end of the hour, in a soft, equal blend of the two outcomes, half decayed, half not, neither more real than the other. The second thing Schrödinger places in the box is a small detector, a device sensitive enough to notice when a radioactive decay has occurred. This is a very ordinary sort of instrument in a physics laboratory, a small, quiet listener that pays attention for the specific soft signal of a decay event. If the atom decays, the detector notices. If the atom does not decay, the detector notices nothing. Perfectly reasonable. The third thing Schrödinger places in the box is where the thought experiment quietly turns strange. He connects the detector to a mechanism, a hammer poised above a small glass vial. The vial contains a poison. If the detector notices a decay, it triggers the hammer, which falls onto the vial, which breaks. The poison is released into the box. And then, inside the box, at the far end of this whole gentle apparatus, Schrödinger places a cat. Let this land softly. The cat, in this thought experiment, is entirely tied to the fate of the single radioactive atom. If the atom has decayed, the detector has fired, the hammer has fallen, the vial has broken, the poison has been released, and the cat, unfortunately, has not survived the hour. If the atom has not decayed, none of this has happened. The vial is intact, the hammer is still, the poison is undisturbed, and the cat is, presumably, curled somewhere at the back of the box, quietly wondering why it has been placed inside such an odd piece of furniture. Two outcomes, perfectly clean, perfectly linked. The atom decays, the cat is gone. The atom does not decay, the cat is fine. There is no ambiguity in the mechanism. The connection between the tiny quantum event and the very large classical creature is deliberately straightforward. Now here is the piece where the thought experiment does its quiet work. At the end of the hour, before anyone opens the box, what does quantum mechanics say about the state of the atom? It says the atom is in a superposition, half decayed, half not decayed. Not that we simply do not know which, not that there is a hidden fact under the cup. It says the atom, right now, unmeasured, is a genuine blend of both possibilities. That is what all the equations of quantum mechanics, without exception, tell us. That is what the double-slit experiment demonstrated. That is the whole meaning of the wave function we met in the last part. But if the atom is in a blend of both possibilities, and the atom is connected to the detector, and the detector is connected to the hammer, and the hammer is connected to the vial, and the vial is connected to the cat, then by the same gentle logic, everything downstream of the atom must also be in a blend. The detector must be in a blend of having fired and not fired. The hammer must be in a blend of having fallen and not fallen. The vial must be in a blend of having broken and not broken. And the cat, quietly, must be in a blend of being alive and not being alive. That is the sentence the thought experiment was written to produce. Read it slowly, because it is one of the strangest sentences in the history of physics. Before the box is opened, the cat is in a superposition of alive and not alive. Not that we do not know, not that the cat is one thing that we have not checked, not that there is a fact under the cup we simply cannot see. In the same soft sense that the electron was not really at one slit before being watched, the cat, if quantum mechanics applies all the way up, is not really in one state before the box is opened. It is in a genuine blend of two states, one of which involves a living, breathing, curled-up cat, and the other of which involves a cat that is no longer able to be curled or to breathe. Both possibilities are equally present. Neither has been chosen. And only when the box is opened, only when the world outside interacts with the world inside, does the wave function quietly collapse and one of the two outcomes become the actual one. This is deeply uncomfortable. It is meant to be. That is the whole point of the thought experiment. Restate this softly. Schrödinger did not, at any moment, believe that real cats live in blended states of being alive and not alive. He was not proposing this as a theory of feline biology. He was not suggesting that the universe actually behaves this way at the scale of animals. What he was doing was gently pointing out something uncomfortable about the logic of quantum mechanics as it was being described by his colleagues. If the equations really apply to everything, and if superposition is a real feature of the world before measurement, then there is nothing in the equations to stop this soft blend from scaling up. There is no natural cutoff. The atom, the detector, the hammer, the vial, the cat, all of them are made of atoms. All of them obey quantum mechanics. If a single atom can be in a blend of states, then in principle the whole chain of connected objects can be too. And that includes the cat. The thought experiment was designed to make that consequence uncomfortable, to take the strangeness that felt safely contained at the scale of the very small and to link it by an ordinary sensible mechanism to something at the scale of the very ordinary, to ask gently and pointedly whether the standard interpretation of quantum mechanics really wanted to say what it seemed to be saying. Because if it did, then it was saying quietly that the cat itself was not a definite creature before the box was opened. Schrödinger's own view was that this was a problem. He felt that the standard picture, taken to its logical conclusion, produced something absurd, and that the absurdity was a signal that the standard picture was incomplete. Something else, he suggested, must be happening. Something must intervene somewhere along the chain to prevent large objects from ever really being in blended states. Something must, softly, keep the world of cats and boxes definite, even while the world of atoms remains blended. He did not know what that something was. He did not have a mechanism to propose. He was, in his gentle way, raising the question. Other physicists, at the time, took the thought experiment differently. Some accepted the strangeness. Some suggested that the collapse of the wave function happened whenever an interaction reached a certain size or complexity. Some suggested that the collapse happened only when a conscious observer looked, though this interpretation has become less popular over time and involves its own difficulties. Some suggested that no collapse ever happens at all, and that both branches of the cat's wave function continue on, in some soft mathematical sense, forever. That last suggestion has grown into an entire family of interpretations in modern physics, though we are not going to walk through them tonight. What matters for us, in this quiet part, is that the thought experiment did exactly what Schrödinger meant it to do. It made the strangeness impossible to ignore. You cannot easily dismiss superposition as a curiosity of the very small if the very small is directly linked to the fate of a cat. You cannot easily say that only atoms behave that way if a mechanism connects an atom to something you care about. You have to either accept that the cat really does live, briefly, in a blend of states before the box is opened, or you have to explain why not. And that explanation is exactly what physicists have been working on, gently and patiently, for the 90 years since Schrödinger first put a hypothetical cat in a hypothetical box. We will meet part of that explanation in the next section of tonight. There is, as it turns out, a rather beautiful, quiet reason why we do not see cats or cups or coins living in blended states in ordinary rooms, and it does not require any special magic or any collapse of the equations. It has to do with the fact that a cat is not actually isolated from the world in the way the thought experiment assumes. But that is for the next part. For now, let the thought experiment stand as an invitation, not a resolution. It is not there to give you an answer. It is there to give you a feeling, a soft, uncomfortable feeling. The feeling of noticing that if quantum mechanics really is the way we have been describing it, then somewhere along the chain from a single atom to a whole cat, something has to give. Either the cat is a blend, or the equations are incomplete, or something we have not yet identified is quietly acting to keep the large world definite. Something must be doing that work. The question is what? Sit with that for a moment. It is one of the loveliest open questions in all of physics. Where does the blend end? Where does the single answer begin? At what scale? In what conditions? By what mechanism does the wave function collapse? Is it the size of the object? Is it the number of atoms involved? Is it the presence of an observer? Is it the complexity of the interaction? Is it decoherence, which we will meet next? Is it something we have not yet named? These are not just philosophical questions. They are questions that quiet, careful physicists work on every day in laboratories around the world, using very small pieces of equipment, trying to build systems in which superposition can be maintained for as long as possible in objects as large as possible. Quantum computers, in fact, are one of the most active research programs where this question matters, because keeping quantum states in superposition without collapsing them is exactly the challenge that has to be solved. But even setting aside the technology, the philosophical point of the cat remains. It is the calmest possible reminder that the strangeness of the small world does not politely stay in the small world. It is connected by ordinary mechanisms to the large world, and the question of where and how the strangeness ends is not a solved question. It is a very open, very gentle, very ongoing conversation in which some of the smartest people in the world are still, in their patient way, participating. Schrödinger's cat has become, in the many decades since it was first proposed, a kind of quiet mascot for this whole cluster of questions. The cat has appeared in books, in cartoons, in t-shirts, in coffee mugs, in the names of student physics societies. It has been referenced in novels and in television shows. It is very possibly the most well-known animal in the history of physics, which is again a lovely legacy for a creature that has never had to leave the page. There is something warm about that. About a hypothetical cat in a hypothetical box, living a hypothetical existence that has done more to introduce ordinary people to the strangeness of quantum mechanics than perhaps any other single idea. And perhaps, in some soft mathematical sense, the cat is still in there, still curled at the back of the box, still both alive and not alive, still waiting quietly for someone to open the lid and in doing so, gently choose one of the two possibilities. It is a very peaceful sort of immortality. The cat does not have to be one thing or the other, because it is neither. It is a symbol, it is a question, it is a soft insistence from Schrödinger to us that we not look away from the tension. So we are not going to look away. We are going to sit with the tension for a little longer in this quiet part of the night and let the question rest on us softly. If a single particle can be in a blend of states and a cat depends on that particle, then where, precisely, does the blend end and the single answer begin? Where is the line? What is the mechanism? Why do we, in our ordinary rooms, with our ordinary cups and lamps and shoes and sleeping animals, never see anything living in a blended state? The next part of tonight will begin to answer that question. Not perfectly, not completely, but gently, because the answer, when it comes, is one of the loveliest and quietest pieces of modern physics, and it is the reason your room, in all its calm definiteness, is still able to feel like a room at all. So we come to the part of tonight where the tension the cat left us with begins, gently, to ease, not by resolving itself completely. The deep questions Schrödinger raised have not been fully answered, and there are still corners of the argument that physicists are quietly working on today. But there is a beautiful piece of modern physics that has, over the last several decades, done an enormous amount of the work. It is one of the softest and loveliest ideas in the whole subject, and it explains with real elegance why your cup is on the table, why your cat is either sleeping on the chair or padding across the floor, and why the strangeness of the small world does not, in ordinary rooms, spill upward into the large one. The idea is called decoherence, and it is what we are going to spend this part of the night with. Before we walk into it, though, we should notice something about the setup of Schrödinger's thought experiment, something we softly passed over in the last part, but which is doing a great deal of quiet work in the story. The box. The whole thought experiment depends on the box being perfectly sealed, not just sealed in the sense of being closed, perfectly sealed in the deeper sense that nothing about the state of the atom or the detector or the hammer or the vial or the cat is allowed to leak out. No information, no warmth, no light, no sound, no gentle nudge of any kind that could tell the outside world what was happening inside. The atom's superposition is only allowed to propagate up through the chain to the cat if the whole chain, including the box itself, is treated as one clean, isolated system. If anything inside the box is communicating in any way with anything outside the box, then the story quietly changes, and it changes in a way that turns out to matter enormously. Because in real life, boxes are not perfectly sealed. Nothing is, not even close. Consider, for a soft moment, what an ordinary room is actually like. Not the tidy, quiet picture your mind hands you. The real physical situation. In your room, right now, the air is full of molecules, trillions upon trillions of them, drifting, colliding, tapping softly against every surface. They are landing on your skin. They are settling onto the walls. They are pressing very gently against the wooden leg of the table, the ceramic side of the cup, the metal of the shoe's small buckle, the fur of the sleeping animal on the chair. This tapping is happening at a rate so vast that no words in ordinary language quite reach it. Every square inch of every surface in your room is being touched by air molecules, quietly and constantly, billions of times per second. It has been happening since you sat down. It has been happening since long before you sat down. It is happening, of course, right now. And it is not only air. There is light, too. The lamp beside your sofa is sending photons into every corner of the room. Some of them are hitting the cup. Some are hitting the shoe. Some are landing on the sleeping animal. Some are, in truth, gently touching you. The photons are so soft that you feel nothing when they arrive. But they arrive in enormous numbers, every moment, bouncing off every surface, landing on everything. Even in a dark room, photons of infrared light, the soft warmth that every object gives off simply by existing at any ordinary temperature, are drifting between everything and everything else. Warmth is leaking from you into the blanket. Warmth is leaking from the lamp into the air. Warmth is leaking from the wall into the room. Warmth is leaking from the sleeping animal into the chair. The whole room is a soft web of gentle interactions, most of them invisible, all of them constant. Now think about that soft phrase from the last part. Measurement, we said, is anything that would let anyone in principle know what a particle is doing. It is not about human eyes. It is not about human awareness. It is about interactions that carry information out into the world in ways that would allow the state of the particle to be, in principle, discovered. And here is the very gentle, very important thing. Every one of those tiny interactions in your room is, in the technical sense, a small measurement. Restate this carefully. When an air molecule taps against the side of your cup, it bounces off in a slightly different direction depending on exactly where the cup is. That direction is, in principle, information about the cup's position. It leaks out into the room. It is carried by that one tiny air molecule out into the vast tangle of the surrounding environment. When a photon lands on the sleeping animal on the chair, it reflects off in a way that depends on the exact shape and position of the animal at that instant. That reflection is, in principle, information about the animal's state. It leaks out. It is carried away by the photon into the air, into the room, into the world. Every one of these interactions is a small nudge, a tiny question, a very soft asking of a very small piece of the world, where it is and what it is doing. And the environment quietly, constantly, is asking these questions everywhere in your room, of every object, every fraction of a second, at a rate that is genuinely difficult to imagine. Which means that a cup, or a cat, or a shoe, or a sleeping animal, or the lamp beside the sofa is not actually isolated the way Schrödinger's box was pretending to be. Not even close. A cat in a real box is being constantly touched by air, by photons, by warmth. Information about its state is constantly leaking out. If the cat was somehow, briefly, in a superposition of alive and not alive, the difference between those two states would be enormous. The molecules of the air would be moving differently in each case. The infrared warmth given off by the cat would be different. The tiny vibrations of the air, the small breath, the shape of the fur, all of it would differ. And all of these differences would be immediately, constantly, endlessly, leaking out into the environment through countless small interactions. Decoherence is the name physicists give to the process by which those countless small interactions gently destroy superposition in large objects. The word itself is, admittedly, a little clinical. It sounds like something a very tired doctor would murmur while looking at a chart, but the idea it names is beautiful. Coherence is the technical name for the special condition in which a quantum system is able to hold on to its superposition, in which the different possibilities in the wave function can still interfere with each other, in which the strangeness of the small world is fully present. Decoherence is the loss of that condition. It is the process by which a quantum system, through interactions with its environment, gradually and irreversibly stops being able to maintain the interference between its possible states. It does not require anyone to look. It does not require any dramatic collapse. It is simply the quiet consequence of a system being touched, softly and constantly, by a warm, noisy world. And here is the astonishing thing. Decoherence is fast. For any object, even remotely the size of ordinary things in your room, decoherence happens so quickly that no experiment could ever hope to catch a superposition of two visibly different positions. If a cup could somehow be prepared in a superposition of being on the left side of the table and being on the right side of the table, the interactions with the surrounding air and light would collapse that superposition in a time so brief that we do not have ordinary language for it. Far faster than any moment, far faster than any thought. So fast that, for all practical purposes, the collapse would already be finished by the time you finished imagining it. The cup, before you even had a chance to notice, would be on one side or the other, definite and calm. This is why we never see cats living in blended states. This is why your cup is on the table. This is why your shoe is by the door. This is why the sleeping animal is on the chair. It is not that the underlying particles have stopped being quantum. It is not that the electrons in your cup have stopped, on their own, being spread out possibilities. It is that the cup, as a whole, is made of so many particles and is so constantly interacting with its environment that any attempt at maintaining a large-scale superposition is instantly undone by the trillions of tiny measurements happening every moment. Let this reassure you. The cup on the table really is on the table. The animal on the chair really is on the chair. You are not going to open your eyes and find your shoe scattered across the hallway in a soft cloud of possible shoe positions. Decoherence has been quietly doing its work in your room for as long as your room has existed. It is what makes ordinary life possible. It is what makes the world feel solid. It is why your intuition of definiteness, the calm background comfort we started this video with, is reliable at your own scale. Because at your own scale, superposition simply cannot last. The environment is too warm, too noisy, too constant. Definiteness is the natural state of large objects in ordinary rooms, not because the equations demand it, but because the environment enforces it tenderly and continuously by never once looking away. Restate this gently. A cat in a real box is being measured constantly by everything around it, whether anyone opens the lid or not. The air molecules are measuring it. The photons are measuring it. The warmth is measuring it. In the quantum sense, there is no such thing as an unmeasured cat, because the cat is always in contact with its own environment, and that contact carries information away in every direction. The superposition of alive and not alive simply cannot survive the noise of a real box. It collapses silently and quickly into one outcome or the other, long before anyone thinks of opening the lid. The thought experiment worked only because Schrödinger, entirely reasonably for the time, was allowed to assume a perfect isolation that turns out to be, in the real world, unachievable. This is one of the loveliest quiet corrections in the history of physics. Not that Schrödinger was wrong, he was making a philosophical point, and the point still stands, but that the standard equations of quantum mechanics, taken carefully and applied to the real environment in which objects actually live, already contain the reason why we never see cats in blended states. The strangeness stays in the small world not because there is a magical cutoff, and not because the equations break down at some size, but because the everyday world is too noisy for the strangeness to survive at large scales. Superposition is a delicate thing. It needs quiet. It needs isolation. It needs to not be touched. And a real cup in a real room is being touched in the smallest and softest possible ways, so constantly that its superpositions cannot outlast even the shortest imaginable moment. The physicists who worked patiently on this idea across the second half of the 20th century deserve a soft mention. Their names may not be as famous as Schrödinger or Heisenberg or Bohr, but their contribution has been enormous. Hans-Dieter Zeh, a German physicist, was one of the first to think seriously about decoherence in the early 1970s. He noticed that if you took quantum mechanics seriously and applied it not just to a small system, but to the system plus its environment, the equations already predicted the disappearance of superposition at large scales. He wrote about this for a long time, patiently, while much of the physics community was busy with other things, and his ideas were slowly recognized as central to understanding how the quantum world becomes the classical one. Later, physicists, including Wojciech Zurek, a Polish-American physicist working in the United States, developed these ideas further. Zurek, in particular, spent decades thinking carefully about how information leaks from quantum systems into their environments, and how the environment, in effect, selects out certain stable states that survive contact and others that do not. His work helped clarify why we see the specific classical world we do, and not some other. The cup is not just definite. It is definite in familiar ways, at familiar positions, obeying familiar physics. Decoherence, in his gentle framing, is what makes the classical world classical. There were others too, working quietly in various institutions, refining these ideas, checking them against experiments as the experiments became possible. In the last few decades, physicists have actually begun to catch decoherence in the act, watching in real time as small quantum systems, kept as isolated as possible in laboratory conditions, lose their coherence through interactions with their environment. These experiments are difficult and delicate. They require temperatures near absolute zero, isolation from stray photons, shielding from vibrations, careful control of every possible source of disturbance. But they work. They show, very directly, that decoherence is not a philosophical handwave. It is a physical process. It happens. It can be measured. It can be slowed down. It can be studied. And when it happens, superposition really does disappear, exactly as the equations predict. This last part is worth staying with for a moment, because it connects the whole story to something that has been much in the news over the last several years: quantum computers. The whole engineering challenge of building a quantum computer is, at its heart, the challenge of holding on to superposition. A quantum computer works by keeping small quantum systems in carefully controlled blends of states, allowing those blends to evolve through calculations in ways that would be impossible for ordinary computers. But to do this, the small systems must be kept, as much as possible, from being noticed by their environment. Any stray photon, any errant air molecule, any tiny vibration, any small nudge of warmth is a small measurement, and every small measurement is a small step toward decoherence, which is why quantum computers are kept in extraordinarily cold, extraordinarily isolated, extraordinarily quiet conditions, refrigerators that reach almost to absolute zero, vacuum chambers, shielding against every kind of external influence. And even then, the coherence of the quantum systems inside can only be maintained for a short time before it slips away, because the world, even a very quiet world, is never quite quiet enough. There is something rather lovely about this. The very thing that makes ordinary life feel solid and definite is the very thing that makes quantum computers so hard to build. The environment measures. The environment collapses. The environment enforces definiteness. In your room, this is a blessing. It is why your cup is on the table. It is why your evening is calm. It is why the world beneath the world does not spill upward into disorder. But for someone trying to build a machine that uses the strangeness of the small world to do useful work, the environment is a gentle enemy. Every whisper of warmth is an obstacle. Every drifting photon is a small betrayal. So the physicists who build quantum computers have become, in a very real sense, artisans of isolation. They spend enormous care making sure that their little systems are not noticed. They protect superposition the way one protects a candle in a windy room. And still, in almost every case, the wind eventually finds a way through. Decoherence eventually wins. The blend collapses into a single answer. The calculation, if it has finished by then, produces a result. If it has not, the coherence is lost, and the calculation has to be started again. But let us come back to your room, because your room is not a quantum computer. Your room is the opposite of a quantum computer. Your room is warm and noisy and gently full of interactions in every direction, at every moment. Your room, for the deep quantum machinery inside every object, is a place of constant conversation. The air is asking the cup where it is. The photons are asking the shoe where it is. The warmth is asking the sleeping animal where it is. And the cup and the shoe and the animal, being large and complex and warmly embedded in the environment, answer immediately, definitely, in ordinary classical language. They are here, they are there. They are on the table, by the door, on the chair. These answers are being given softly and continuously, without anyone having to be in the room to hear them. That is perhaps the strangest and gentlest image of the night. A room full of quiet measurements, constant small conversations between air and object, between photon and surface, between warmth and everything else. No one is doing them. No one is asking. There is no observer with a clipboard. There are no dramatic experimental setups. There is only the ordinary noise of an ordinary room, softly enforcing definiteness on everything within it, second after second, moment after moment, forever. Your cup is on the table because the air keeps noticing. Your shoe is by the door because the photons keep landing. Your sleeping animal is on the chair because the warmth keeps flowing. The definiteness of your world is not a fact that just is. It is a fact that keeps happening. It is being made quietly, all the time, by the very environment we spend most of our lives ignoring. Decoherence is the reason. It is the quiet mechanism by which the strangeness of the small world stops at the doorway of the ordinary one. It is why Schrödinger's cat, in any real box, is not really in a blended state. It is why the world you can see and touch and love and rest inside is stable and solid and predictable, even though the pieces it is made of, on their own, are none of these things. There is one soft last thing to notice before we let this part come to rest, and it is a small piece of humility. Decoherence explains beautifully why we do not see superposition at large scales. It explains why the coherence disappears. But there is still a very quiet remaining question, one that lives at the very heart of this story, and which physicists continue to work on today. Decoherence explains why the wave function of a large system loses its ability to interfere with itself. But it does not, on its own, fully explain why exactly one outcome is what we end up seeing, rather than the whole spread of possibilities in some soft mathematical superposition still. That final small piece, the transition from a decohered blend to a single definite answer we actually experience, is still, in some interpretations, an open question. We will not push into it hard tonight, but it is worth softly noting that even this beautiful mechanism, decoherence, is not the complete answer to the whole tension the cat opened up. It is a very large piece. It is not, perhaps, the whole picture. We will let that rest, as we let so much rest tonight, gently. For now, though, close your eyes and imagine your room as it really is. Not still, not silent, full of quiet measurements, full of soft interactions, full of gentle, constant noticing. The cup is on the table because the room, in a very real and very tender sense, keeps noticing where the cup is. The animal on the chair is on the chair because the world will not stop paying attention. Definiteness is not the natural state of the underlying particles. It is the natural state of a room that never stops watching itself. And beneath all of it, in the very quiet layer where the particles actually live, the strangeness remains, softly and completely. Nothing has changed for them. They are still spreads, still possibilities, still not committed to positions. It is only and always the warm, gentle noticing of the environment that pulls their spread into a shape we can see. Without the noticing, the world would loosen back into possibility. With the noticing, it holds itself softly in the shape of an ordinary evening. A cup, a lamp, a shoe, a blanket, a sleeping animal, a room quietly full of measurements, keeping itself gently definite for you. So let us come back softly to the room where we began. The cup is still on the table. The lamp is still beside the sofa. The shoe is still by the door, exactly where you kicked it off, or exactly where you kicked it off in whatever room you happen to be resting in tonight. And the sleeping animal, if there is one in your life, is still curled on the chair, or the rug, or the corner of the bed. Nothing in the room has moved. Nothing in the room has changed. The evening has continued to be an evening. The air has continued to be air. The lamp has continued to give its soft, steady light to everything within reach. And yet, in the very quiet way that certain kinds of understanding change a place without disturbing it, the room is now, in some small sense, different than it was when we began. Not because anything has physically shifted, but because you now know something about it that you did not know before. You know that the definiteness of these ordinary objects, the calm background comfort of one thing in one place at one time, is not simply a given fact of the universe. It is not a property that the particles carry on their own. It is something the world keeps making, softly and constantly, by never once looking away from itself. Restate this gently. Beneath the ordinary surface of your room, in the very small layer where the atoms and the electrons and the photons live, no one is committing to a position. The pieces of your cup are not, on their own, on the table. The pieces of your lamp are not, on their own, beside the sofa. The pieces of the shoe are not, on their own, by the door. And the pieces of the sleeping animal on the chair are not, on their own, on the chair. Each of these particles, considered in isolation, is a spread of possibilities. Each is a soft wave function, drifting through its own quiet mathematics, uncommitted, unresolved, unwilling to be a single small thing in a single small place. What holds them in place, what pulls their gentle spreads into the shape of an ordinary evening, is not their own preference. They have no preference. What holds them in place is the environment, the endless soft touching, the photons drifting in from the lamp, the air molecules pressing quietly against every surface, the warmth leaking gently from one object to another. Every one of these small interactions is a soft measurement. Every soft measurement is a small nudge toward definiteness. And the room, in its warm, ordinary way, is producing so many of these small nudges every fraction of every second that the pieces of your cup have no choice but to arrange themselves into a cup-shaped, table-sitting, quietly present thing. Not because they want to, because the room will not stop noticing. This is a very strange thing to know, and it is a very peaceful thing to know, and it is worth sitting with in both of those registers at once. It is strange because it means the solidity of your room, the calm reliability of everything in it, is not the deep default of the universe. The deep default of the universe, in some sense, is possibility. Spreads, blends, uncommitted arrangements, wave functions that do not, on their own, resolve into single answers. The classical world you can see and touch and love and rest inside is a kind of surface effect, a soft shimmer that appears only because everything is constantly being touched by everything else. If, somehow, the touching stopped, the room would quietly loosen, not fall apart, not dissolve, just loosen, gently, back into the spread of possibilities it had always been underneath. And it is peaceful because that touching is happening right now. It has been happening all evening. It has been happening since long before you sat down. The air is drifting. The photons are landing. The warmth is flowing. The room is doing its constant quiet work of holding itself together without being asked, without needing anyone to organize it. The definiteness you rely on is being produced continuously, tenderly, everywhere in your room by the ordinary noise of an ordinary place. You do not have to do anything. You do not have to keep watch. You do not have to remind the world to be solid. The world is reminding itself in every fraction of a second, in every corner of your evening, without ever growing tired, which is, in its own quiet way, a rather lovely thing to know about a room, that it is not simply sitting there, that it is, at every moment, softly making itself. Let this settle for a while. There is no rush. The cup is still on the table. The lamp is still beside the sofa. The shoe is still by the door. The animal is still on the chair. The definiteness of these things has never once been a fact carved into the universe. It has always been a moment-by-moment gentle achievement, brought into being by the constant conversation between every object in your room and every other object, and by the drift of air and the fall of light and the leak of warmth that keeps that conversation going. If the conversation ever stopped, even for a moment, the room would gently forget what shape it was supposed to be. But the conversation does not stop. It has never stopped. It will not stop tonight or tomorrow or the night after. It is one of the most reliable features of the universe, and it is happening right now everywhere in your room without you having to think about it, which means you can rest. Now, there is one small piece of humility we should carry with us into the last of the evening, because it is honest, and because tonight has been an honest kind of night. We have spent the last hour walking through a picture that many physicists find beautiful and satisfying, superposition as a real feature of the world, wave functions as smooth spreads of possibility, measurement as the moment when a spread becomes an answer, decoherence as the quiet mechanism by which the strangeness of the small world stops at the doorway of the ordinary one. This is the picture most working physicists use most of the time, and it works. It matches the experiments. It predicts the results. It gives us the tools we need to build our lasers and our microscopes and our slowly maturing quantum computers. But when you ask the deeper question, the question the cat first opened, of what exactly happens at the moment of measurement, of why we experience a single answer rather than a spread, of where precisely the switch from blend to definiteness lives, physicists are still very quietly disagreeing. There is nothing wrong with this. It is not a crisis. It is not a sign that the physics is broken. The mathematics continues to work regardless of the interpretation you prefer. But there are, in the community of quiet, careful thinkers who work on these questions, several different ways of understanding what is really going on, and it is worth softly touching on them, not to resolve them tonight, but to notice that they are there, gently, in the background of everything we have said. Some physicists think that decoherence, the beautiful mechanism we met in the last part, is essentially the whole story. That once the environment has thoroughly measured a system, there is nothing further to explain. The system is, for all practical purposes, in a single state. Any leftover mathematical whisper of the other possibilities is so completely tangled with the environment that it can never come back, and so it might as well not exist. In this view, the collapse of the wave function is not really a separate event. It is a very fast, very thorough, very irreversible spreading of information into the environment, and the appearance of a single outcome is what that spreading looks like from the inside. This is a soft, calm view, and many physicists find it satisfying, or at least sufficient. Others take a slightly different position. They notice that decoherence explains beautifully why we do not see interference between different possibilities at large scales, but that it does not, on its own, explain why we, as observers, experience one specific outcome rather than another. If the wave function never really collapses, if the mathematics simply keeps evolving smoothly, then in some sense all of the possibilities continue on, and there is a family of interpretations growing out of the work of a young American physicist named Hugh Everett in the 1950s that takes this seriously. In this view, the wave function really does not collapse, ever. The possibilities do not disappear. They simply branch away from each other, softly, so that in each branch, a version of the world with a single outcome continues to unfold. In one branch, the atom decayed and the cat did not survive. In another, the atom did not decay and the cat is fine. In one branch, the electron went through the left slit, in another, through the right. Neither branch is more real than the other. They simply, quietly go their separate ways, and each of them contains a version of us who sees only one of the outcomes and never notices that the other exists. This is a strange view. It is also a strangely elegant one, in that it needs no special act of collapse, no mysterious switch, no separate rule for measurement. The mathematics simply keeps doing what the mathematics does, and the branching structure of the possibilities is taken seriously as a description of the world itself. Some physicists find this deeply satisfying. Others find it uncomfortable or unnecessary or philosophically odd. But it is a real view held by real, thoughtful people, and it is one of the ways of understanding what tonight's strangeness might really be. There are other interpretations too, quieter ones, less famous ones, in which physical mechanisms are proposed for collapse, or in which additional hidden variables are added to the theory, or in which the whole idea of an objective external world is gently questioned. We are not going to walk through all of them tonight. There are, if you count them carefully, more than a dozen distinct interpretations of quantum mechanics that have been seriously entertained by working physicists, and new ones continue to appear as new experiments become possible. This is a very active area of thought. It is not settled. It may not be settled for a long time. What is settled, however, and what we can carry gently into the rest of the night, is this. The equations work. The experiments confirm the equations. The strangeness is real. The particles that make up your room do not, on their own, live in single positions. The environment, through countless small measurements, keeps them arranged into the classical shapes you can see. And beyond that, the deeper questions about what is really happening at the moment when a spread becomes an answer are questions that physicists are still calmly and patiently working on. It is one of the loveliest ongoing conversations in the history of science, and it will continue long after tonight is over. You do not need to resolve it. You never needed to. The physicists themselves have not resolved it, and they have been thinking about it, in some cases, for their entire careers. What you can do, softly, is let the question rest alongside everything else in your evening. Let it be one more quiet presence in the room. Let it lie there beside the cup and the lamp and the shoe and the sleeping animal as one of the things that exists tonight without demanding an answer. Because the room itself, whatever the deep interpretation, is doing its work. That much is not in doubt. The air is drifting, the photons are landing, the warmth is flowing. The particles are being softly measured by everything around them, and their spreads are being tenderly pulled into the shape of ordinary evening things. Whatever the metaphysics turns out to be, the physics of your room is producing a solid, reliable place for you to rest in. Definiteness is being made, moment by moment, at every point in the space you occupy. You are held inside it. You have been held inside it all evening. Let us return one last time to the picture we started with, because tonight has been a slow, gentle spiral, and it deserves to come to rest where it began. There is a room. There is a cup on the table. There is a lamp beside the sofa. There is a shoe by the door. There is, perhaps, a sleeping animal on the chair, or the bed, or the rug, and there is you, wherever you are, hopefully warm, hopefully comfortable, hopefully able to keep your eyes closed for as long as you like, without needing to follow the words too carefully anymore. The room looks exactly as it did when we started. The objects are all in their ordinary places. The intuition of definiteness is still there, doing its background work, letting you know without effort that everything is where it is supposed to be. You have not lost that intuition tonight. It was never in any danger. It works. It has always worked. It will continue to work for the rest of your life. But you know, now, something small and gentle about how it works. You know that the definiteness of your room is not simply given, that the pieces of your cup, the pieces of your lamp, the pieces of your shoe, the pieces of the sleeping animal are all, on their own, uncommitted spreads of possibility. And you know that the room, in its warm, quiet, ordinary way, keeps those spreads gently arranged into single answers, by never once stopping the soft flow of interactions that fills every corner of every ordinary space. The room is looking at itself. That is what it has been doing all evening. That is what it has been doing all your life. Every wall, every surface, every drifting molecule of air, every quiet photon from the lamp, every soft leak of warmth from your skin, is a small piece of the room, noticing another small piece of the room. And out of all of that noticing, out of that endless tender attention that no one has to do on purpose, the ordinary world assembles itself, moment by moment, into something you can rest inside. If you like, you can hold that thought as you drift. You do not have to. But if it helps, it is a thought that has been quiet company for a lot of people over the years. The idea that the solidity of the world is not a stubborn, immovable fact, but a kind of ongoing gentleness. That the room around you is not passively there, but is actively and softly making itself present, again and again, in the small, unnoticed rhythm of everything touching everything else. There is something warm about that. It suggests a universe that is not lonely, even in the parts where no one is looking. Everything is being attended to. Everything is being kept. You are being kept too. The particles that make up your body are being softly measured by the air around you, by the fabric of the blanket, by the surface you are resting on, by the warmth of your own breath drifting slowly in and out. You are being held into a single you, moment by moment, by the same quiet mechanism that holds the cup on the table and the shoe by the door. It is a very ordinary miracle. It has been happening every second of your life. It is happening right now. So, the world is still here, the room is still here, the cup is still on the table, the lamp is still beside the sofa. Everything you love, everything you know, everything you might miss if you drifted off in the middle of this sentence, will still be exactly where it is when you wake up. Nothing has changed. Nothing needs to change. The world will keep looking at itself for you, gently, without pause, all through the night. And beneath it all, in the softest possible layer, the particles will continue to be their own strange selves. Spreads, not points. Possibilities, not answers. Held only by the tender, endless noticing of the ordinary world above them. That is the deep, quiet secret tonight has offered you. That definiteness is not a given. That the solidity you rely on is being made at every instant by a universe that will not stop paying attention to itself. You can let this settle now. The thinking part of the evening is over. The lamp is still on. The cup is still there. The animal on the chair is still breathing softly in whatever imagined room your mind has kept for it. The shoe is by the door. The blanket is still around you, or nearly around you, or somewhere nearby waiting to be pulled up a little more. The room is holding itself together gently without needing to be asked. The particles are being watched by the air, by the light, by the warmth. Everything is being kept. The world is still looking at itself. The world will keep looking all night. You can rest softly now. The lamp is on. The cup is there. The room is quiet. The world is watching softly, so you do not have to. Good night.